Welcome to the Deep Dive. Today, we're digging into something that, well, it powers pretty much everything we do, but we almost never think about it. And honestly, my own journey with this started with a bit of confusion.
Oh?
Yeah, years ago, I saw ads for that movie Transformers. And in my head, Transformer meant one thing, those gray boxes you see on power poles.
Right, the electrical one.
Exactly. So I thought, wow, a movie about electrical equipment? That's different. I actually went expecting, I don't know, a documentary maybe.
Slight chuckle. You got giant robots instead.
Giant robots turning into cars. Total surprise. But it does show how that word gets used, doesn't it?
It really does. And you're definitely not the only one who's made that connection. The word transformer or Yuzande in Korean, it just sounds like big change, right?
Yeah.
Like a total makeover. The movie plays on that big action-packed idea. But in our world, the world of electricity, when we say transformer or maybe electrical transformer, we mean something very specific. Still vital, maybe even more vital day to day than giant robots, I'd argue.
Okay, I think I'd agree with that. Less explosions, though.
Hopefully.
Yeah.
Its job is to transform, yes, but in one very particular way. Changing the voltage. The electrical pressure, basically.
Right. And that's exactly what we're diving into today. These electrical transformers, the real ones, they're kind of the unsung heroes, hidden in plain sight, making our modern world tick.
Absolutely. They are the backbone. Without them, getting power from, say, a dam hundreds of miles away to your phone charger. Impossible. We'd be stuck with very local, probably very inefficient, and frankly, unsafe power.
So that's our mission for this deep dive, then, to really unpack these things.
That's the plan. We want to cut through any confusion, robot-related or otherwise, and give you a clear picture. We'll explore what they are, why they're so incredibly important for everything, from the huge power plants right down to that little charger brick.
And we're aiming this at, well, anyone who's curious, right? Beginner-friendly.
Exactly. We'll keep it clear, straightforward, avoid the super heavy jargon, but still get into the details. By the end, you'll have a solid understanding, a real appreciation for these devices working silently all around us.
Okay, sounds good. Let's get into it then. Setting the movie robots aside, firmly aside, what is an electrical transformer at its core? Like the simplest definition.
Okay, at its absolute most basic, an electrical transformer is a static device. That means no moving parts inside, which is pretty cool.
Right.
And its job is to change the magnitude of voltage, the size of the voltage, in an AC or alternating current circuit.
Voltage?
Yeah.
That's like the electrical pressure, you said.
Exactly. Think of it like pressure in the water pipe.
Right.
The transformer doesn't make the electricity. That's a really common misconception. It doesn't generate power.
Ah, okay.
It just takes the electricity that's already flowing and adjusts its pressure, its voltage level. So it's more like a pressure regulator or a special valve in that water pipe analogy. It can make the pressure higher or lower, but the water has to be flowing already.
I like that. A voltage height adjuster
Yeah.
or a voltage translator that clicks. It's just modifying that pressure.
Precisely.
Yeah.
It's all about changing that potential.
And is that why we have different names for it? I've heard people say transformer, obviously, but also electrical transformer and sometimes just trans. Are those all the same thing?
Yeah, they pretty much are. It just depends on the context, really. Transformer is the general everyday term everyone knows.
Okay.
If you want to be super clear, especially, given the movie, you might say electrical transformer or do.
Right, to distinguish it.
Exactly.
Yeah.
And then, yeah, within the industry or just talking casually, if you know the tech, people often shorten it to trans. It's just shorthand, like saying fridge instead of a refrigerator.
Gotcha. Shows how common they are, I guess.
It really does. They all mean that same static box whose job is changing voltage.
So if that's its job, adjusting voltage, why do we even need to do that? Can't the electricity just, I don't know, stay at one voltage level the whole way? Does it really matter?
That's probably the most important question here, because the answer is why transformers are absolutely essential. The electricity itself might not care about voltage, but everything else does.
Like what?
Like the power plants generating it, the wires transmitting it hundreds of miles, and definitely the phone or the toaster using it. Every single part of that journey works best, most efficiently, and crucially most safely at a specific voltage.
Okay.
You just cannot take the super high voltage power from a generating station and plug your laptop into it. It would be, well, messy. Instantly.
Right. I can picture that like the fire hose on the orchid analogy you use.
Exactly like that. Destroy the orchid, waste a ton of water, and probably cause some chaos. Sending power needs the right pressure for the right task. And think about transmission. Sending power over long distances, you get really high voltage. Why? Because it's way more efficient. It reduces energy loss.
Okay, efficiency, that makes sense.
But then using that power in your home, you need low voltage.
Yeah.
Much, much lower for safety and because your appliances are designed for it.
So high for sending, low for using.
That's the basic idea. Without transformers acting as the go-betweens, the translators, the whole system just wouldn't work. Or it'd be incredibly wasteful and dangerous.
That safety versus efficiency point feels really central. Matching the voltage pressure is everything. Can you give us a really concrete example, something maybe, people have actually bumped into?
Oh, definitely. The classic one is traveling or buying electronics online from another country.
Ah, yeah, the plug adapters.
Well, sometimes more than just the plug adapter. Imagine you buy, I don't know, a really cool coffee maker online. It ships from the US, let's say. It arrives, you're excited, but then you see it's designed for 110 volts. But you live here in, say, Korea or Europe, where the wall outlets are 220 volts.
Right. Big difference.
Huge difference. You absolutely cannot just plug that 110V coffee maker into a 220V socket. Best case, you trip a breaker. Worst case, poof, smoke,
Yeah.
dead coffee maker.
Been there, maybe, with a hairdryer once.
It happens. So what do you need? You need a transformer, specifically one that lowers the voltage.
Okay.
It takes a 220V from your wall, steps it down to 110V, and then you plug your coffee maker into the transformer. Now works perfectly, safely. That little box is doing the voltage translation right there on your countertop.
So that's a real-world transformer in action. Makes sense.
And the other way around, too, I guess. If I took my 220V hairdryer to the U.S.
Exactly the same principle, just reversed.
Yeah?
In the U.S., with 110V outlets, your 220V hairdryer wouldn't work properly to be underpowered, maybe not even heat up much.
Right.
So you'd need a transformer that raises the voltage. It takes the 110V from the U.S. wall outlet and steps it up to 220V for your hairdryer. Okay, step up versus step down.
Precisely. That dual capability is what makes them so vital for global compatibility, for making sure things work safely everywhere, like a universal translator, but for electricity pressure.
So if they can raise voltage or lower it, they must have different names, right? We don't just call both transformers.
You're thinking exactly right. We need to be specific. And yeah, they have names that make perfect sense once you hear them.
Lay it on me.
Okay, first type, the step-up transformer. In Korean, that's ki sung apki. Think sung sung, like rising or ascending.
Step up. Makes sense.
It increases the voltage, takes a lower voltage in, puts a higher voltage out, steps at UP. You find these right near power plants, usually.
Got it. And the other one?
The other one is the step-down transformer. In Korean, gang up, gang implies lowering or descending.
Step down, okay.
This one does the opposite. It decreases the voltage, takes higher voltage in, puts lower voltage out, steps it down. These are everywhere else, basically, bringing the power down to usable levels.
Okay, that's super clear. So, back to the travel adapter thing. My U.S. coffee maker, 110V, in my Korean kitchen, 220V, needs a...
Step-down transformer, because you're stepping the 220V down to 110V.
Perfect. And my Korean hairdryer, 220V, in a U.S. hotel, 110V.
Yeah, step-up transformer, stepping the 110V up to 220V.
Got it. Step up, step down. Makes total sense. It's like gears on a bike, almost. Higher gear for speed, lower gear for climbing.
That's a fantastic analogy. Yeah, different voltage gears for different parts of the electrical terrain transmission versus usage. You need the right ratio for the job.
Okay, now this is where, for me, it starts getting really mind-blowing because it's not just about travel adapters, is it? You said these things are everywhere in the power grid.
Oh, yeah. Everywhere.
How does that even work? Getting power from some giant power plant, maybe way out in the countryside, all the way to my apartment in the city. It can't be just one wire, one voltage, right?
Not even close. It's an incredible journey, honestly. A multi-stage, highly engineered process. Think of it like a long-distance relay race, but for electricity. And almost every handoff point in that race, there's a transformer, changing the voltage, either stepping it up or stepping it down. It's this constant adjustment that makes the whole thing work.
Wow. Okay. Walk us through it from the start.
All right, let's trace the path. Stage 1, generation and the big step up. It all starts at the power plant. Could be coal, nuclear, hydro, solar, wind, whatever. They generate electricity, but not at the super high voltage needed for long trips.
Right.
So right there at the power plant, or very close by, there are massive step-up transformers, huge ones. Their job is to take the generated voltage and boost it way, way up.
How high are we talking?
Extremely high. Think hundreds of thousands of volts, like 765,000 volts at 765 kilovolts, or 765 kiloV, sometimes even higher.
Whoa, 765 kiloV, that sounds intense and kind of scary. Why so high? Just brute force.
It sounds counterintuitive, right? More voltage sounds more dangerous, but there's a brilliant reason. Efficiency. It's all about fighting energy loss.
How does high voltage help with that?
Okay, quick physics bit. When electricity flows through a wire, there's resistance. Resistance causes energy to be lost as heat. Like a wire getting warm.
Sure.
The amount of power lost as heat depends heavily on the current, the amount of electrical flow, not the pressure. Specifically, it's proportional to the square of the current. So double the current, you get 4 times the energy loss.
Okay, so you want low current for long distances.
Exactly. And here's the magic. For the same amount of power delivered, if you dramatically increase the voltage, the pressure, you can dramatically decrease the current, the flow.
Oh, I see. High voltage means low current for the same power.
Precisely. By stepping the voltage way up to 765 kV, they can send huge amounts of power over hundreds of miles with much, much less current. And less current means way less energy wasted as heat in the transmission lines.
So those giant towers carrying lines across the country, they're carrying super high voltage, low current electricity.
That's exactly right. It's the most efficient way to move bulk power over long distances. Trying to send it at household voltage, most of it would just turn into heat before it got anywhere useful.
Okay, that initial step up makes a lot more sense now. It's about efficiency over distance. So what happens next? It can't stay at 765 kV forever?
Nope. Once it gets closer to where people actually live and work, the stepping down process begins. Stage 2. Regional substations. The electricity arrives at these big facilities called main substations. You often see them on the outskirts of cities, big yards full of equipment, buzzing noises.
Yeah, I think I know the kind of place. High fences.
Exactly. Inside, there are large step-down transformers. Their job is to take that ultra-high 765 kV transmission voltage and knock it down significantly, maybe down to something like 154 kV. Still very high, but more manageable for regional distribution.
Okay, so first big step down from 765 kV to 154 kV. Still way too high for my house, though.
Absolutely. Still far too high.
Yeah.
So the journey continues closer to you. Stage 3. Local substations. Now, as the power lines spread out into towns and neighborhoods, the electricity flows into smaller local substations. These might be more tucked away, maybe a brick building or a smaller fenced-off area.
Right.
Here, another set of step-down transformers takes that 154 kV and brings it down again, often to something like 22.9 kV or maybe 13.8 kV, depending on the system.
22.9 kV, okay, getting lower. Is that what's on the poles in my street?
Getting very close. That 22.9 kV is often the voltage running along the main power lines on the taller utility poles in your area, or sometimes buried underground. It's the distribution voltage for the neighborhood or district, but still, way too hot to handle for your appliances.
So there's another step.
There's one final crucial step down, and this one happens literally right in your neighborhood, maybe even right outside your window.
Okay.
Stage 4, the pole transformer. That gray canister, usually cylindrical, hanging near the top of the utility pole.
Yeah, the gray box thing. I see them everywhere.
That's a transformer. A step-down transformer is the last stop on the main grid.
No way. I've seen thousands of those and just never really knew what they did.
Most people don't. But it's doing an incredibly important job. It takes that 22.9 kRV from the local distribution line and steps it down one last time to the voltage you actually use in your home. Typically 220V in many places, or maybe 120V, 240V in North America. It might also provide 380V for some larger buildings or businesses nearby.
Wow. So that little gray can is what makes the power safe to come into my house.
Exactly. It's the final gatekeeper, translating that medium distribution voltage into the safe, usable voltage for your lights, your TV, your fridge, everything. Without that pole transformer, you couldn't plug anything in.
That's actually amazing. The final step down right there on the pole, mind blown.
It's pretty neat, isn't it? Such a vital piece of infrastructure just quietly doing its job. But wait, this story doesn't necessarily end quite there. Well, think about what happens inside your house. Stage 5, adapters.
Yeah.
The tiny transformers. You've got 220V coming out of the wall socket, right?
Right.
But what about your laptop, your phone charger, your router? Do they run on 220V AC?
No. They have those power bricks, the adapters.
Exactly.
Yeah.
Those adapters are doing another transformation. They're not grid transformers in the same sense, but they contain circuitry that acts like a miniature step-down transformer. They take the 220V AC alternating current from your wall and convert it down to a much lower DC direct current voltage that your sensitive electronics need, maybe 5V for a phone, 19V for a laptop, something like that.
So even the little charger brick is a transformer, kind of.
In function, yes.
Mm-hmm.
It's performing that final super localized voltage step down and conversion to make the power suitable for that specific device. It's the very last link in that incredibly long chain.
So putting it all together, it's this constant chain reaction. Step up massively at the start for efficient travel.
Right.
Then step down, step down, step down as it gets closer.
Mm-hmm. Regional, local, right on the pole.
And then even step down again inside my gadgets with adapters.
You've got it. It's this continuous, carefully managed cascade of voltage changes, mostly stepping down, that allows us to use power generated hundreds of miles away, safely and efficiently. It's a silent symphony of transformers.
Wow. Okay. So we've talked about step up and step down and how they both play these critical roles. But, in general conversation, maybe among people who work with this stuff, when they just say a transformer, referring to the power grid, the is there one type they usually mean more often?
That's a really sharp question. It gets into the practical language, the nuance. And yes, you're right. While both types are absolutely essential, the system literally wouldn't work without both step up and step down.
Right.
In the day-to-day context of the power system, especially the parts closer to consumers, when someone just says transformer, they're most often referring to a step-down transformer, the ones doing the SOU, lowering the voltage.
Huh. Why the focus on step down?
It's mostly a numbers game, really. Think about the journey again. You've got maybe one huge step-up stage right at the power plant. Critical, yes, but geographically limited.
Okay.
But then you have step down happening at regional substations, then again at numerous local substations, and then literally millions of those pole-top transformers, plus all the transformers inside buildings for specific equipment, and arguably billions of adapters.
So there are just vastly more step-down transformers out there in the system, especially closer to where we use the power.
Exactly. The sheer quantity and the frequency with which engineers, technicians, and even consumers interact with voltage reduction stages means that transformer often becomes shorthand for step-down transformer in practical terms. They're the ones you see, the ones that need maintenance in neighborhoods, the ones directly feeding power into homes and businesses.
So while step-up is vital for starting the journey efficiently, step-down dominates the landscape and the everyday operations of the grid near us.
That's a perfect way to put it. Understanding that helps you understand the common lingo and where the focus often lies in distribution and usage. It's that silent majority again.
Right. That's actually really helpful for getting the bigger picture. It's not just about definitions, but how it all plays out in practice.
Exactly. It moves you towards being really in the know.
Okay, so let's try and wrap this up. We started with my cinematic confusion about robots versus electrical boxes.
Huckles. A memorable start.
And we've ended up tracing this incredible, complex journey of electricity, all made possible by these transformers. It's kind of amazing how fundamental they are, yet so invisible in our daily thoughts.
It truly is one of the great unsung marvels of modern engineering. So just to recap the key takeaways. Transformers are the essential voltage managers. They adjust the electrical pressure.
Right. No moving parts.
Static devices. Two main types. Step up for boosting voltage. Crucial for efficient long-distance travel from power plants.
Minimizing those energy losses.
Exactly. And then step-down transformers, which do the vital work of lowering voltage progressively, making it safe and usable for everything from city grids down to your home appliances.
They're the crucial links ensuring power gets from A to B safely and efficiently.
Couldn't have said it better. They facilitate that whole complex path. And yeah, don't forget the little guys, the adapters for your phone, your laptop. They're mini transformers doing the final vital step down right where you use the device.
It really changes how you look at things. So maybe a final thought for everyone listening. Next time you plug something in, or you just happen to look up and see one of those gray cans on a utility pole, what clicks now? What new questions pop into your head after this deep dive?
Yeah, and maybe think about this. Our whole world runs on this system, this delicate chain of voltage changes. What happens if a key link breaks, a big substation goes down, or even just your local pole transformer fails? What does that ripple effect look like?
Good question.
We're looking forward. We're bringing more renewable energy online, right? Solar farms, wind turbines, maybe more distributed generation. How does that change the game for transformers? Do we need different kinds? Smarter ones? How does this invisible network have to adapt to keep everything running smoothly? What part of this silent, constant work stands out most to you now?